Hello students, in this video we'll see applications of the weak maximum principle to prove uniqueness of solutions to the diffusion equation and a comparison principle. So let's suppose we have two solutions. U and V to the 1D heat. What do I mean by this? I mean on the finite interval, of course. So this is going to say that the 1D heat is going to be U T is equal to K UXX. That U of 0T, when x is equal to 0, some function, I'll call it phi of T. We have some function U of L of T. I'll call that function psi of T. Those are the boundary conditions when x is equal to 0, x equals psi. And then the initial condition over here, that U of x and 0 is, let's say, some function f of x, right? That's the 1D heat equation boundary conditions. So here we have the situation. There's my spatial condition. So in other words, the function u is going to be equal to what over here? It's going to be equal to psi over here. It's going to be equal to phi over here. And it's going to be equal to f over here, right? That's 0, that's L, and this is t capital, right? That's the t-axis, and so this is my domain for the heat equation over here, okay? Excellent. And note, since this is linear, differences of solutions is also solution. Difference of solutions is a solution. In other words, I can take U and V that both solve this problem over here and subtract them and get another solution, right? And so therefore, what would that, so if I let W be U minus V, then W solves, it solves WT is equal to K WXX with what boundary conditions? Well, of course, I'm going to subtract off phi minus phi is just going to be 0. So W of 0T is equal to W of LT is equal to W of X and 0, and all those values are equal to 0, right? And so now by the weak maximum principle, what can we say? We can say the maximum of W over this region, over 0 to L cross 0 to T, is the same as the max of W on the boundary of that region. Moreover, it can occur at T capital, right? We already proved that from the weak maximum principle. But the maximum of those things is equal to 0. So the maximum of W is equal to 0, and then likewise, similarly, the minimum of W by the minimum principle on this region, 0L cross 0T, like that, right? And so that implies that W is identical to 0. So W of X and T is identically equal to 0, and therefore U of XT is identically equal to V of T, and therefore the solutions to this problem are unique. So solutions to star are unique. Great. Okay, so we proved that there are unique solutions to star over here, right? Moreover, what can we do? So moreover, let's prove a comparison principle, right? So what's the comparison principle going to say? Comparison theorem. Okay, so suppose I have two situations over here. So I have UT is equal to K UXX with initial conditions U of 0T, U of LT, and U of XT, U of X, 0 are all given. Those are given to us. And then I also have this over here, then I also have VT is equal to K VXX with V0T, VLT, and then Vx0 given. Okay? And what does the comparison theorem state? The comparison theorem states the following. It says if U0T less than or equal to V0T, ULT less than or equal to VLT, and U x0 less than or equal to vx0. So if if the conditions for v majorize the conditions for u, then u of xt less than or equal to what? Less than or equal to v of xt, right? All right, in other words, u minus v is always negative, right? Good. So in other words, we can do the same thing over here now. What I can do is I can say, let's define, here's the proof of this fact. We're going to do the same trick. If I define w to be just u minus v, right? Then all of w's initial data is less than 0. Then w0t less than or equal to 0, wlt less than or equal to 0, and wx0 less than or equal to 0. And w satisfies what? I know that w and wt is equal to k wxx. So by the weak maximum principle, I know that the maximum of w occurs on the boundary. Well, the maximum w occurs on the boundary means that the maximum is less than or equal to 0. So if the maximum is less than or equal to 0, that means that w is always less than or equal to 0 by the maximum principle. And if w is always less than or equal to 0, that says that u minus v is less than or equal to 0, which proves that u of xt is less than or equal to v of x of t. So I get two things for free from the weak maximum principle. I get that there are unique solutions to the diffusive equation. I also get there's a comparison principle that if I have two solutions to the diffusive equation, and the initial conditions for one of the solutions always majorize the other one, then the other solution, the solution with the larger initial data, will always majorize the solution with the smaller initial data. That's the comparison principle for the heat equation. Thank you very much.